This video is going to look briefly at the structure of ionic compounds. I would recommend just before you watch this that you are familiar with what ionic bonding is. I've made a video on that. And I've also made a video about dot and cross diagrams which show the electron structure of the different ions in ionic compounds. What we're going to look at now is a little bit different. We're not looking at the electron structure of the ions, we're looking at how the ions themselves arrange themselves. And it ends up being fairly similar to in a metal. I've made a video about that, but it'll be a little bit different for reasons that we'll see. So I've got here counters to represent the different ions. So these are positive metal cations, these are negative non-metal anions. The positives will all repel each other, so they'd want to be far away from each other. And the negatives would all repel each other as well and want to be far away from each other. But positive and negative opposites attract, so positives want to be close to negatives. So the pattern that they'll end up making is one where they alternate, and by alternating we get the maximum attraction between the ions. And this is what ionic bonding is, which I explained in that other video. We call it electrostatic attraction. That's what holds ionic compounds together. In reality, it's a 3D structure, so we've got billions of ions going in rows and in columns and in the third dimension as well. But we can't show that very easily in a diagram, so we draw a 2D slice of it. And just to look closely, each positive metal cation is surrounded by negative non-metal anions, and each anion is surrounded by cations. So that's how we get the maximum attraction. So if I was going to draw that, it would look quite similar to how I showed it with the counters. I'll just draw it nice and big. I'll show the ions close together. I don't need to draw any more than just 3 by 3. And by doing that, I can show that alternating pattern. I'll label that these are the cations. These are the anions. The easiest and most common example of an ionic compound is sodium chloride, which we commonly just call salt. And that's made of sodium cations, Na+, and chloride anions, Cl-. We call the structure a giant ionic lattice. It's a giant structure because, remember, this is just a tiny section. It's got billions of ions going in the different dimensions. It's ionic because the particles in it are ions, cations and anions. And it's a lattice because the word lattice describes that structure where you've got rows and columns. Just very briefly, 2 things you could do to this structure. This is showing a solid because it's got ordered ions that aren't able to move. But of course, if you melted it, think back to particle theory, then those ions would be able to move over each other and they'd then go in a random order like that. The other thing that ionic compounds tend to do is they're soluble in water, so you can get them to dissolve. And the reason why they dissolve is because water molecules are polar, and you don't need to know what that means, but the effect it has is the water molecules are attracted to the cations and the anions. So the water molecules, when you drop some salt in water, will surround each of the ions because they're attracted to it, and by doing that they'll pull those ions away from each other and they'll break the lattice. So we'll end up with the ions surrounded by water molecules, and it's energetically favourable for that to happen, which is why it does, and you end up with those ions having been separated from each other. So in both cases, by melting it or by dissolving it, those ions get pulled away from each other, the lattice breaks, and the ions are free to move around.